So I'm going to try and explain some of the core cryptography methods through the usage of web pages and JavaScript. So we'll cover symmetric key encryption, a little bit about key wrapping, and then look at the signature methods of ECDSA, EDDSA, and HMAC. Then we'll have a look at elliptic curve Diffie-Hellman and X25519, and then finally we'll look at RSA signing and encryption. So all the examples should be on this page here if you want to use them. So you should be able to just go onto the page and then easily add in some text. We have a key and an initialization vector here. Then that will produce a salt value for that cipher, and then we'll get the decrypted value. Hopefully it should always give you the right decrypted value, or we should verify the signature. Okay, so the way that this works is that I've just used two elements for the boxes. So the pre allows for non-editable text here in the HTML page, and I've also used a text box or a text area here. Okay, there's my text area, and I've just modified the style for that to be this. So the text area is just a little bit bigger for the font so we can actually see it. But you can see it just makes the layout of the page look a little bit nicer, and the user can quickly see where they need to enter the text in here, and they should be able to enter text into those elements there. Okay, so this is my setup here. I've got a button here that will reload the page and reload the keys, but most of the time we can just type in our text. Then, as I said, we've got these pre elements here and given us a name. There's a key, cipher, decipher. Okay, so all I'm going to do here is to generate a key, put into that pre. Then I'll create the cipher whenever the user enters a character into the text area, and then automatically we'll decipher that. So the JavaScript that relates to this is using this code here. Okay, we have a generate key. In this case, it's AES GCM, and we can use 128, 192, or 256 bits. And then for each key, we can actually define if it's going to be used for encryption and or decryption. We can export the key using this method here, and when we await, it will stop and await for the reply back from the function. And this is a JSON web token format that we're using, and that format is this format here. Okay, it's just a useful way to display our keys. I'll explain that a little bit later. This is the encrypt message. We get the message, and then basically we create an initialization vector or a salt value for our encryption, and then we can just encrypt using the encrypt method here with our key and with our encoded data. So the encoded data converts the ASCII values into byte values, because with encryption we deal with byte values. Okay, then to decrypt, it's roughly the same. We just use the decrypt method with the ciphertext and the key, and with the initialization vector that we've used, and then we can actually show the result. This inner text property here is used within the pre HTML tag. Okay, so there's a function called update, so that calls up the encrypt message and decrypt message, and that is caused whenever the user actually changes the message box here. So for every character, then it will call up this update and we'll get that refreshed. Okay, so basically what's happening here is that every time a character is pressed, then on input event, it will call up update, and that's why we're seeing it changing here. Okay, so that's the setup there. Only other thing is that I've just got a little script that makes the message value equal to hello123 whenever the user opens the page overall, you can see here. Okay, and then I just add that. Right, so that's the explanation of the code that I've used, and you'll find the code here for a basic explanation. Okay, so the first simplest methods that we're going to look at is to use symmetric key encryption. And so with the symmetric key encryption, both Bob and Alice use the same key. One of the most popular methods that we use is Galois counter mode, or GCM. That converts the block cipher into a stream cipher, and it makes it fast in its operation. So in this case, this is our key here that we're generating. We can see the key type there. The actual secret value is this K value here. It's converted into base 64. And obviously we can use it to encrypt and decrypt. This is the salt value that we're going to be using. So we can use the same key. And the good thing is that whenever we create a new cipher, then we will create a new initialization vector for it. The size of that initialization vector we just saw in the code a little minute ago. If I can try and find it again for our IV. Just let me try and locate it on the page. There we go. It's 16 bytes, which is 128 bits. So that's a 128 bit salt or initialization vector value, and that produces this cipher here. And when we decrypt, we get this back. The thing to notice about using GCM is that the length of the GCM cipher varies directly with the text that we have, or the plain text. This is because it's a stream cipher and not a block cipher. I'll show you a block cipher in a little minute. Okay, so that's ACM GCM mode, the most popular. If you can, make sure that you always use 256 bits for our key here. So another method that we can have for symmetric key is cipher block chaining, or CBC mode, and this is a block cipher. So what we'll notice here is that the cipher is not changing in its length, but then all of a sudden it jumps. So we went from 1 block to 2 blocks. Again, we'll keep going until we get to another 16 characters, and then it jumps again. Keep going, the cipher block length stays the same until we fill up another block. With CBC, we use what's called padding, and we add the padding to the blocks as they go in, and then we cipher 16-byte or 128-bit blocks at a time. On receiving that, when we decrypt it, we've got to get rid of the padding at the end too. But you can see it works okay, and even if we've got one character there, then we're getting a 16-byte block there, and then whenever we fill up that block, then it creates a new one. Okay, so in the code, all we do is that this time we're using AES CBC 256-bit key, and there's no other changes really that we have. The salt value stays the same, 128 bits or 16 bytes, and everything is really the same as the last code that we saw, just that we're now using a block cipher. And okay, CTR is another method. In this case, we have what's called a counter. So the counter is an initialization for the blocks, and then for each block we increment the counter, and it gives us some degree of security. So again, this is a stream cipher as its output, so we can see that the cipher is varying with the input text here. Okay, so in this case now what we're doing is creating a counter value. So it's roughly the same as an initialization vector, the same size, but we use it in here for our counter value. Okay, so that's the three main methods here. And then if we have a password on our to generate a key, we can use what's called PBKDFS2. So with this, it takes a passphrase or a secret phrase, and then we'll convert it into a key that we can then use to encrypt. Okay, so this is just a simple web page that we can actually encrypt our data. So there's the key that we create from PBKDFS2. We have a salt value, and we have our initialization vector. So we take the password and the salt value, and it produces this key. We then take that key and an initialization vector for AES, and we'll create our encrypted text. So I've just created this in base64, and hopefully when we decrypt it, we'll get the value back again. Okay, so PBKDFS2 is useful when we're using not a random key generation, but something that's from a password. One method that we can use to be able to protect our keys is what's called key wrapping. So with key wrapping, what we have is that we'll take a key, such as this symmetric key here, GCM, and then we create what's called a wrapping key. So the wrapping key will actually encrypt our target key, and this is producing this wrapped key here. So we would need this key here to be able to decrypt that back to get the original key. You can see what we've done here. We've actually done the decryption or the unwrapping here, and we get the original key back, which is the same as this one here. So the code for this one slightly different. In this case, we generate the key that we're going to protect, and then we generate our wrapping key here. So you can see this is the wrapping key that we're going to use, and this is the key that's going to get wrapped in there, called key. And we have wrap key. Then we'll do a wrap key, and we'll take the key, and we'll take the wrapping key, and then we'll implement the wrapping process. After that, we can then unwrap the key to take the wrapped key and the wrapping key, and then to be able to recover it back into a GCM 256-bit key. Okay, so hopefully when we try this a few times, then we'll always get the same key returning back in there. You can see we get different wrapped keys, but the key that we get back should always be the same as the key that we wrapped. Okay, so now look at signatures. So with signatures, a common signature method is with ECDSA, and this uses elliptic curve cryptography. For a standard curve, we typically start at 256 bits, which is a P256 curve, and then we have a hashing method for our data, such as SHA-256. So SEPT256 key 1 is used for Bitcoin and Ethereum, and SEPT256R1 or P256 is used in most applications, such as probably within this web connection here. Okay, so in this case, hopefully it should work again. So this is actually updating to verify, but with our hashing, with our signature method, we take our data, we take a hash of it, such as with SHA-256, and then we use elliptic curve to be able to create our signed data. This is the signature. If you're interested, it's an R and an S value that we have, and you can see it's quite a small value for our signed data. So the keys look like this. So this is the public key in a JWT format, and here is the private key. So the public key has an X and a Y point on the curve, and the private key has a D value, which is a scalar value. So when we take the base point, which is G, and then we multiply it by D. It's not really multiplying, it's adding the G point D times. Then we get the public key value here. So the private key also contains the public key if we want it to, but the main private key is this D value here. So that's then used to be able to create our signature. We can also represent the keys and the signature in what's called a PEM format from the data. This just makes it easier to copy and paste our data rather than having binary data. Okay, though the code in this case, what we have is that we can have a sign data method, and this is just calling up the sign method, and to verify there we can see we're using ECDSA and SHA-256. We sign with the private key and then we prove with the public key. So that's the verification process. These methods here are just converting our binary into base 64 so that we can actually show our keys and our data in a base 64 format. Okay, so here's the key generation that we have. ECDSA and P256 is the curve that we can have. We can have higher values for the P curves, which will give us more security if we need it. Okay, so same code roughly as the last time, and we get our signature, and then this is showing that it's actually working here. Okay, so just a simple example there. This is a higher level curve here. So in this case, we're using P512, and this time we get larger values for our keys. Okay, so that's ECDSA. So now let's look at HMAC. So with HMAC, what we have is we have a shared secret key, and we'll use that to sign a hash of the data. So unlike public key encryption, where we sign with the private key and prove with the public key, in this case we only have one key that will sign and then verify. Okay, so this is the signed data that we have here. So we can give it a try, and hopefully it will always give us a true here. So the key itself this time is a secret value of K. That's our key. And we're using HMAC 256 for the method that we're implementing. Okay, so for the signing, we sign a certain type of hash with our private key, and then we verify again with our private key. So the private key is actually put into the verification process, if we can see it. So we need to find the update function here. Okay, so there's the signed data. So we can see here we're using that key, and we're using the same key here to be able to verify it. Okay, so that differs from public key encryption. So in this case, because we use the HMAC, it's the same key that actually signs and verifies, and that is created here. As I said, we're using SHA-256 and HMAC to be able to sign. The true here means that the key is exportable, and in many circumstances we would set that to false because we don't want the key to be viewed in any way. So that's the HMAC function there. Okay, so here's just a simple example here, and we can see here there's the key, that's created. There's the signature for HMAC, and then we're verifying it and here. Okay, so the third method that we can use for RSA is to be able to sign with RSA. So we used elliptic curve DSA or ECDSA to sign with elliptic curve. We can also use RSA to sign. So one of the most basic formats is PKCS 1.5. Okay, in this case, we'll be generating our keys. So this is showing us our public key and our private key for this method. So the way that that's structured is that we start with two prime numbers. We multiply them together to get a modulus value here. So n is equal to p times q. We have a public exponent value, and then we derive the decryption exponent d from that value. So our public key is E and N, and our private key is D and N. And for that, we basically perform a simple operation. We take the cipher to the power of E, the message to the power of E, to give our cipher, and then we take the cipher to the power of D, and we'll get our message back again. And each of these is mod N each time. Okay, so that's the key. So the key itself in our JWK format, we can see here the public key has this value here. This value is 65,537. And then we have our n value. We convert our base 64 into an integer, we'll get that value back. And then we have our n value. So this can be distributed to anybody. But then our private key has the d value, which is this one here, which is going to do the decryption, and n, which is the mod n. It has all the other things in there like dp and dq because they help to speed up the decryption process. Okay, so the code is much the same as the other ones that we've seen. There's our gen key, that's the signature method that we're going to use. The size of the modulus, that's n, made up of two prime numbers of 1024, and then we have a hashing method for this method here. Okay, so that allows us to be able to generate our keys, and I've just converted them into this PEM format. Okay, so let's try signing. So here's the signed data overall, and we can see that works in there. Okay, so there's the keys that we're generating. I've shown them in JWT format and also PEM format. This is the most popular that we would get, and we can just import that. But increasingly, we're using JWT format for the keys. Okay, so overall, we will sign with our private key, which is this one here, and then we'll prove with our public key, this one. Okay, so we can do that manually if we want, convert it to hexadecimal, and we can see that works. Okay, we can verify that too. Okay, so that's one method of signing with RSA. Another method is with PPS. So with PPS, we have provable security, where with this PKCS 1.5, we don't have that provable security. So for PSS, so we'll generate some keys for that. So the keys look very similar overall, as we saw with the other key pair generation. And then we'll give this a try. For our signatures. Okay, so there's the signature there in hexadecimal, and we can verify, and that works. Okay, so similar to the other RSA one, but this time we're using RSA PSS, and PSS has a salt value. Every signature has a different output. If we have the same data and the same keys with PSS with a salt value, we'll get what's called a non-deterministic output for the signature, where it will actually change each time for the same input. Okay, so that's the basics of our signing methods. Now let's look at key exchange. With key exchange, we often use what's called elliptic curve Diffie-Hellman. So in this case, what we have is we have a key. Bob generates B and generates a point on the curve BG. Alice generates A, creates a point on the curve AG, and then they exchange these BG and AG values. Bob multiplies Alice's value by B to get BAG, and Alice will do the same with her values and gets ABG, and those values should be the same. That gives us the seed for generating the shared key. So the key that we get, so for the private key, we have this D value, which is the secret value, and then that creates a public key point of the X and the Y. So in this case, the public key is then just the public key point. So Bob and Alice would exchange these public key values, and then in the end, we end up with the same shared key. So in this case, we're going to create an AES GCM key, 256 bits, and this is the key example here that we've actually created. Okay, so we can regenerate the keys, and we should see that the derived key for both Bob and Alice will be the same each time we generate these keys. So let's try it with some data. Okay, so in this case, what we're going to do is we're going to exchange the keys, and then we're going to encrypt the data between Bob and Alice. This could happen in a session, or it could be a long-term thing that they can exchange public keys and then use the shared same secret key or symmetric key. Okay, so we'll give it a try, and we can see here, this is the cipher that's created from the key that we've generated from this key here. These are the public keys that are exchanged here and here, and from these we're generating this shared key that should be the same. And we can see here, when we run it, we get our cipher. Because we're using GCM, the cipher will vary with the size of the text, not like the block cipher that we used before, because GCM is converted into a stream cipher. Okay, so that works perfectly. Another method that we can use is X25519, key exchange 25519, and this uses a different curve, not P256, but curve 25519. We actually end up with with smaller keys overall, as we can see here, and we don't have an X and a Y value as we had with the P256 curve. This is because curve 25519 only needs the X value stored. So the keys are actually smaller than the elliptic curve ones, the P256 ones. Okay, so there's the private key, there's the secret value D, and then there is the public key point there. So Bob and Alice would exchange the public key values, and then in this case they'll derive the same GCM key. The code is much the same as we've used before. We can generate keys for Bob and Alice, and then we can derive the keys using Alice's private key, Bob's public key, and then the other way around overall. Okay, and you should see, hopefully, that the derived keys should work. So now let's try as we did before with the elliptic curve Diffie-Hellman, P256. We'll see if this works, and it does. We can decrypt. Okay, so Bob and Alice have exchanged their keys overall, and then they've used the derived key to encrypt the data. So in this case, we're using X25519 rather than elliptic curve Diffie-Hellman to do that key exchange. Okay, so that's X25519 overall. Okay, so the last area that we're going to cover is using RSA for encryption. So with RSA, we can use OAEP, or optimal asymmetric encryption padding, to be able to encrypt data with the public key and then decrypt it with the private key. Okay, so we have our OAEP 256 keys generated here, roughly the same as the other RSA keys that we created, but now we actually have padding and a salt value that's created for the cipher each time. Okay, so with signing, we signed with the private key and then verify with the public key. With encryption, we encrypt with the public key and then decrypt with the private key. Okay, so if Bob is sending to Alice, he will use Alice's public key to encrypt. She will decrypt with her private key. When we're looking at signing, then Bob signs with a hash of the message with his private key, and then Alice will prove that with his public key, or verify. Okay, so that's our keys generated there. So now we can actually try to encrypt data with public key encryption, and we can see that that works perfectly. This is the encrypted data here converted into a base64 format, and then that's been encrypted with the public key, and then we can decrypt with the private key. Okay, so there's there. We take the public key to encrypt, and then the private key will decrypt there. Okay, so the code, similar to what we saw before, we're getting our keys generated here. Okay, so that will be the key pair that we're going to use, and then we use the we will use the public key to encrypt. If we can find it. So here we go. Encrypt data here. We're using the public key to encrypt, and then we're using the private key to decrypt, and everything should be fine. Okay, so hopefully you can actually see the power of this, especially when it's running in with JavaScript. Okay, so that's been a basic introduction to using this web cryptography integration for JavaScript. If I summarize, basically we integrated symmetric key encryption where Bob and Alice use the same key. We can use a stream cipher such as GCM, or we can use a block cipher such as CBC. We can use PBKDFS2 if we want to generate the keys from a password. And if we want to protect those keys, then we can use key wrapping, which will encrypt the key. Then we looked at signature methods for public key encryption. So that was ECDSA and also EDDSA. These will use the private key to sign, and then the public key is used to verify. We can also use our HMAC for signing, and that will use the same symmetric key for both Bob and Alice. RSA has two main methods for signing: PKCS1 version 1.5, which will create a deterministic signature, and PSS, which creates a non-deterministic method because it uses a salt value in there. Then we looked at our key exchange with ECDH and X25519, where Bob and Alice create a private key, then create a public key, they pass the public keys, and then derive a secret key based on that. We can use that for encryption once we've generated the symmetric key. And for RSA, we can also use public key encryption using OEAP to be able to encrypt data. Again, for this, we take the public key and then decrypt it, to encrypt and then decrypt with the private key. Okay, thank you.